So with that, I welcome Suraj, who will talk about work he has done on reinforcement learning with two agents competing against each other, right? And where is he? There you are. Applause. Mike, sorry, there.
Okay.
Let's
Check. Hello? Yeah. Cool. So I did my studies at Uppsala University, and this was my thesis. So in this thesis, when I began, it was like with the whole curiosity into knowing what machine learning was all about, and trying to figure out by myself and with the help of school what I could do with it. And since I was very passionate about games, I thought that would be a really cool place, and that fits very well into how reinforcement learning is, like the ideas and like say the philosophy is to gamify things and to look at everything from a particular perspective. And it's in a complete change of pace from what we were speaking earlier about semi-supervised learning, because I will walk you through some of the slides. So as you know, here it's called, so the thesis was called reinforcement learning for a hunter and prey robot. And the idea here is that it's a cat and mouse game, and we have a hunter that takes up after the cartoon character Tom, say, and the hunter tries to anticipate where the prey is. That's what the hunter is meant to do. And the prey, on the other hand, is trying to evade the hunter. So that's the kind of adversarial problem that I figured sounds cool. Let's throw reinforcement learning at it. Let's throw some of the things I've learned along the way at it and see where it gets me. And so on that quest, the first thing is we'd want a game environment. And so I can show you what I used. So this was by PycoLab, which was one of the game environments released by DeepMind. And I don't know which way is better, but maybe I can show you the code, and then maybe it's best this way. So here we have, I hope you can all see, here we have this game board. And in this game board, we have the hunter, which is in the red color. And I mean, feel free if you want to ask questions, like if something is not clear, and you can clarify it along the way. And so here we have a hunter in the right corner, which I'm moving now on the game board, and we have the prey. And we have set up this simulator environment of a game where we can allow them to play with each other. And so they cannot exit the simulator, they cannot, and they are playing within this constrained environment. And if, say, the hunter is able to creep up on the prey, we end the game. And so this is just like, I just wanted to show you how this plays through before actually delving into how to model this problem, or at least I thought how I could model this problem. And the other aspect of this was also, the goal was to have two robots. So it's not just in the simulations, but how feasible is it to bring these, like everyone is talking about AI, everyone's talking about making it come to life, and so it's like, how can you show that this is possible and you can do these things? And so with the help of the university, I was able to build these two robots and have them be the Tom and Jerry minds in the real world. And yes, so now that we get the game, I mean, obviously this is Stockholm AI, so a lot of people do know what, yeah, sorry? Yeah, go for it.
Yeah, so about the game, is it perfect information, or do they have like a limited field of view with different agents?
So, yeah, that's a good one.
And what's the green?
Exactly, thank you so much. So, the green sphere around it is more like the area of, like, its influence around a particular, the grid spaces around it. So, it was initially, it came about when, so it's like, they do not see each other, first of all. They have no clue where they are to begin with. They don't know the positions of each other, but they do know when one step into the future, if say Tom made a move and Jerry happened to be in a square next to him in that sphere, he gets captured. And the main idea behind that was I had to also do it with the robots. And for the robots, you don't want them crashing into each other, and you might have a lot of other sensors that you would have to attach to be able to record this. And instead, there was a setup where there was a sound sensor. So in a radius of a certain, in a radius, when the other robot makes a bit of noise to enter it, you were able to detect its presence. So that was the idea behind the sphere. And like you said, it's not perfect information. So it's, they don't know, but they do know the keys and they know they can move around. Yeah.
How does the prey win?
Sorry?
How does the prey win?
How does it?
The win. The prey. How
Yeah.
does it win?
Okay, so the prey is winning. That's again a good one. So the prey is winning is so you have to restrict this. You can't just let this go on for infinity. And so the win condition for the prey is the number of times. So you limit the game. So you say, okay, in 50 steps. Again, there's a bit of math I'll walk through later. That you were able to set a mean of the number of steps that you can take, which is a fair number of steps. That limits the number of moves Tom can make to capture the prey. So if the prey escapes within that window, then it comes out as the victor. And so yeah, good. So this part of it is you're trying to have this agent that is in an environment, and you make observations and you take certain actions and you get a reward in return. That's like the whole premise of how you build a reinforcement learning system. And as we were talking, supervised and unsupervised fall more under the category of you're trying to learn from a data set. You have data, you're trying to generalize. And when you're talking about reinforcement learning, you try to push it one step further and you say, okay, we have partial feedback. And when you have partial feedback, you now have this choice of do you want to make the best of what you know until now, or do you want to explore more? Maybe there's a better option. So that's the dilemma of do you want to explore or do you want to exploit? And you push the multi-banded problem a bit further, then you're thinking about, okay, what is the best move I can possibly take at this particular given situation? And here, the decisions that these agents make will directly affect how we acquire the data, and so, which is again pretty different. It's more active form of learning system as opposed to how it works in supervised and unsupervised. And you set up the problem as a Markov decision process, and I'll go into depth. So it's just, you just set up the states, actions, and we're going to do exactly that. And the main goal is that you want to get good performance, and you also want a trade-off between exploration and exploitation. And so when you're setting up, so what I showed you in the simulator, the same idea translates into a grid where you can place all the states you want, and here I've limited to a 6 by 6, and the brown squares are the walls of the simulator. So you cannot choose actions to get there, and you have actions which you use that the agent has in order to move. And when you stitch those two together, you have the transition dynamics, which is if you are in a particular state, if you choose the action east, you will move there with absolute certainty. That is a deterministic environment, as opposed to a stochastic one where if the wind blows, you may not be where you think you are at. But for the sake of the experiments, I had to make sure that it was deterministic in some sense. And yeah, so then you have the you distinguish between model-based and model-free when you know the transition dynamics and the reward function. So in the robotic setup, the whole idea is you look at the map from a top-down perspective and you place the robot on the ground, and then you have the grid cells around it, and you give it its actions, and so moving up, moving down, moving left, moving right translates quite easily for the robot as well. And the next thing, now that we kind of got a concrete idea of how the state's actions and the transition dynamics work, the next most important element is the reward function. So what is your game? What is the whole purpose? Like, so here we have these two agents which we saw in the simulator, and so Tom and Jerry, and the idea was, like you pointed out, if Jerry escapes, then he gets his reward, and Tom gets his negative reward. And again, we had to limit it to a finite horizon problem and have a limitation on the number of steps you take. And so the way for calculating for this particular, for a grid space of this much size, how much can you allow for the number of moves, is you've allowed the agents to randomly move with random walk and see at what points they intersect. So here we have the intersection times, and times in this context is time steps. And you then you do it over 1,000 episodes, and then you say this is again had to be done on a simulator, and you were able to create, you were able to say, okay, the mean is say around 52 steps for a 10x10 board. And once you do that, okay, so here we have a small video of how this looks. Again, ooh. Yeah, so like how this looks in the real world. And you had, again, space doesn't work. So you had the grid space, some accuracy, it's hard. And you had these two moving and trying to, again, you had this perspective on it, and you sort of get the picture of how, right now it's just episode 1, it's just complete randomness, there's no sense in this, but still this is just to show that the setup does work, and at this point there will be sound because it enters, okay, I know what happened. But yeah, you will have sound there where you signal that the episode ended or whatever, and so and then they return back to the initial positions. So the thing with having to do this over an extended amount of time on a robot is really hard, because you can't get real experience that easily. And again, I didn't go for any neural network sort of an approach. This was more tabula rasa. You had tables, you had state spaces, and then you were actually going right at where the numbers come from. And with the greedy approach, which is the most common approach, the classic approach, you try to exploit more than you explore, and so you estimate what you estimate what is the best way you can use your policy, and this is again controlled by the epsilon parameter, which makes it parameterized. And by tuning this, you can say if you start off with randomness, and if you want to have the main if you want to get the real estimate. And the approach that was interesting was the Thompson sampling approach, where you choose a probabilistic model, and you use this strategy in order to sample from the posterior. So you build up on a belief, and you, through time, as you keep increasing the belief of how well it is to act in this environment, the agents choose this. And so what does it look like in practice? Like, so when we have the epsilon greedy agents competing against each other, and at an episode of 2000, you are able to so you're able to so the strategies sort of show themselves, because you're kind of now trying to look at what the policy is and what are they following, and you in this case you see how, say, Jerry is able to move along the corners of the ground and is trying to evade Tom's catch. And yes,
so what agent?
the input
Yeah,
is like, what do you mean?
It knows what state it is in.
Yes,
That's
it
all.
knows what state
Yeah.
it is in, and it knows the action it is taking, and it gets a negative reward or a positive reward based on the signal.
What's included in the state? The position XY on the board, or?
Yes, XY on the board, but then again, it's so they're calculating this separately, and so they're equally unfamiliar of their surroundings. So it's, you just give them a map, and they start getting a positive and a negative feedback
Well, they only have the XY state.
at every turn. Yes.
Yeah, okay.
Yeah.
So one thing that Jerry could learn is to just go circular,
Yeah.
and then a good strategy for Tom would be to go counterclockwise.
Yeah.
And
So
then maybe Jerry would learn the opposite and so on.
yeah, but
Yeah.
but the thing with the greedy approach is that you can see, for instance, you can see with the, so this was again something I figured was a good way to look at the value. So at every so this is up to 2000 episodes. The position at which Jerry finds most reward, where is that position? And so as you see the game playing out, you can see Jerry is finding a position here, and Tom quickly figures out that particular position, and so Jerry changes his strategy, and Tom quickly converges there. And same way Jerry, so he's just switching it up, and this is the epsilon greedy agent that is, so with Jerry you see what they mean by, and the greedy agent is greedy in the sense that it doesn't explore much. It restricts itself to certain states on the grid, and this heat map here translates to the same grid that we have been seeing. So as you let the episodes run out, and view what is this, what intelligence is it that this algorithm is able to achieve. And as you move to the PSRL, the other algorithm that was considered, here we see, this is again Jerry's perspective and this is Tom's, and here we see immediately Jerry is now more aware of his surrounding. Like it knows where it gets its positive reward signal, and there is better exploration compared to how the greedy algorithm works.
Is there any like explanation for this checkerboard?
Yes. So later I realized I thought that was a cool optimization that Jerry figured out. But later I realized that when you set odd or even number of the number of steps you can take, there are only so many places you can be at. Like the way it's connected is that if you give it an odd number, you would have holes in the setup. But then I went in and had that changed, and when I was able to do that, I was able to. Okay, not this one. I think I have it somewhere, but yeah, what you asked is very valid. Initially I thought it was a really cool optimization that maybe it figured out, but it wasn't. It was due to manual error that led to me thinking it was that. Yeah.
Spawns, got it?
Sorry?
Do they spawn in the same place?
Yes, they spawn in the same place. So they start always at the same spot. And if we were to see how these games rolled out with the PSRL algorithm, we can see in this case how like Jerry just stays where he started, and he figures probably that is a really good strategy for him, which might actually be a good strategy. And jumping back to the slides. So that was the greedy agent and the PSRL. Yeah.
Just unclear. Is there any sort of reaction to the other person once they enter each other's? As I understood, this is the field of view, or is it just completely?
It's more. It's
what they do.
Sorry, when they enter. So, if I were to show you this, and if they were to enter into this particular area around it, this is kind of the vision of what it can see, like enlarging the vision, you are able to conclude the game because they're right next to each other in.
So then it's over.
Yeah, it's over.
But then during the game they don't really know each other's positions.
No, they don't.
So it's just predicting the other person's path and then not getting into that path.
Yeah, so it's like through a number of games, this value from different places, the value comes back, and so it knows at these particular positions, like how to play this game out. And so, so with the PSRL, at least the heat map suggests that it is way more, it's way more aware of its surrounding, in the sense that it finds, in Jerry's case, more spaces that it can stay at. And so so for the results, so I thought it would be interesting to have varying epsilon values. So 1 being a random walk and 0.1 being a very greedy strategy. And it so happens that the greediest hunter and the sort of cleverest Jerry, which is more aware of its surrounding, were a very good match in making a very cool game. And for that, so we can here see, as it calls it, the Tom's prowling strategy and Jerry's hiding strategy, which again, only through viewing these games you sort of get an idea of. You see, Tom is doing what you suggested. He's just used to prowling in that same area. And another cool strategy that Jerry discovers is to go and hide where Tom starts off. And where Tom is continuing to circle in his area, thinking this is where Jerry should be, and whereas Jerry is on the other side, hiding away. And I mean and the coolest thing for this is the plot, which sort of explains how these two algorithms sort of how they sort of complement each other, like in the sense that Jerry's very evidently knows that this is an area of the state map that it should not explore, because it has been constantly getting a negative feedback. And whereas Tom, which is the greedy one, is more bent on following the same thing and getting stuck in a loop, so to speak. Whereas Jerry is more aware of how to use the environment to his advantage, which is sort of like the best of how both these algorithms work. And yeah, and so the kind of questions that I was thinking is, so will this work on any map? Can you just drop a trained DOM and will it be able to adapt quickly? And it so happens that everything comes with like a limitation, and it's not so easy to generalize. And here, as I said, we're not talking about any neural networks. It's just tables that you're filling up in order to know what is the best value of the system. And yeah, so it's just designing an RL problem, which is a lot of fun with game environment, and trying to see how it is to have these two to play about. I think that is it. Thank you for having me, and to yeah.
Usually, like, reinforcement learning is really cool for this kind of example projects, but do you know examples where it's used in some real business case?
I've been trying to find such but I mean, as far as I know, I haven't come across like how. Yeah, I mean, I mean, Thompson sampling is one of the approaches they use in Google for the PSRL algorithm, is to find out with AdSense how to place ads, like where they get the rewards. So that would be one of the applications I know of that it is used. But yeah, this was, again, when you talk about reinforcement learning, it's more about constructing a problem and trying to find what's happening. But I didn't know much more about how applicable it is currently, at least. Yeah, it's been a while. Yep, that's about it.
Any more questions?
Okay, now it's not applicable, but where do you see in the future it could be applied in which areas you think it's mostly?
I mean, I've had a lot of ideas about how it could be used,
You
and
don't have to sell them all.
no, it's more about it's more about being curious to know how far you can go. So it's more of that nature than in the business. At least I can't think of any in the top of my head right now. Yeah.
Do you think that in the future computer security, and maybe especially these hacking systems, might be using some reinforcement learning algorithm to probe what works?
Yeah, it's like trying to find patterns in what kind of attacks come in and how to secure yourself from something that you're not prepared for. But yeah, apart from that,
Cool.
I'm not too sure.
Thank you again very much.